All right, in our next video, we're going to kind of combine the different things we've learned in this unit and look at the fundamental theorem of calculus part 2. All right, so we have this continuous function, and let's say capital F of x is the antiderivative of f of x. All right, then it turns out that the integral from a to b of my function is equal to when I take the antiderivative and I plug in b, minus when I take the antiderivative and plug in a. All right, so this is the fundamental theorem of calculus part 2. To figure out an integral, to figure out an area, I take an antiderivative and then plug in my bounds. All right, just one important thing that students tend to get wrong is the top bound happens first. This is normally the bigger number, not always the bigger number. All right, but the top bound happens first, the bottom bound happens second. All right, let's look at some examples. All right, so evaluate negative 2 to 2 of x squared minus 4. If you were to graph this, you would get some parabola, and we wouldn't be able to figure out this area using our normal geometry stuff, and we could only approximate it using Riemann sums. But now what we can do is we can take the antiderivative x squared minus 4. That is going to be 1/3 x cubed minus 4x plus c. And then I can evaluate this. So a lot of times you'll see this in textbooks and on the AP exams that they put this kind of straight up and down solid line. And they say I'm going to evaluate that from negative 2 to 2. So now I know the antiderivative. I want to plug in 2, subtract when I plug in negative 2. That's basically what this line over here means. So the first thing is plug in 2. Times 2 plus c. All right, so that's when I plug in 2. Then I want to subtract when I plug in negative 2. At the beginning, I'm going to get 8 over 3 minus 8 plus c. All right, remember this negative is being applied to everything here, so it has to distribute into each of the pieces. So I'm going to get negative 8 over 3, but that's with that minus sign, it's going to turn into positive 8 over 3. This is going to be positive 8 with the minus sign becomes minus 8. And then plus c is minus c. I don't know why I put a 4 there. There should be a 3. And now I can combine. I get 16 over 3 minus 16. All right, you notice the c's cancel. That should always happen because one just has a c and one will have the minus c. All right, the constants just go away. 16 over 3 minus 16 is 16 over 3 minus 48 over 3. Is that 16 times 3? Yeah, 48 over 3. That's going to give me negative 32 over 3. And that does not simplify, so I can just leave that as my final answer. All right, so this actual area, without doing an approximation, the exact area under this curve from negative 2 to 2 is negative 32 over 3. And again, even though it's an area, it makes sense to have a negative because anything under the x-axis is considered a negative area. So it's okay that I get a negative answer for my final answer. All right, so let's look at another one. Just like when we were doing derivatives, I had to think about when are you doing derivatives and when are you simplifying. All right, it's going to be a lot easier to take the derivatives as individual parts versus things being multiplied together or divided together. All right, so when we're doing this one, what I'm going to do is actually FOIL this out first before I worry about any antiderivative stuff, because this is going to be the exact same as the integral negative 1 to 2 of x squared minus x minus 6. All right, so now I look at these individual pieces, and we've learned with integrals, we can break it up over the minus and addition sign. So this is just multiple small pieces to do my antiderivative. It's going to be 1/3 x cubed minus 1/2 x squared minus 6x plus c. All right, I want to evaluate that, so put that line from negative 1 to 2. All right, so the first thing I'm going to do is plug in 2. All right, so that is when I plug in 2. Then I subtract when I plug in negative 1. Oops. And now I just want to simplify. All right, so when you do all of this, all right, you're going to multiply everything out and combine like terms. You're finally going to get negative 33 over 2, which is similar to our last answer, right, but it's the exact area of this integral on those bounds. All right, so now for this problem, we're going to look at ways to kind of make our life easier when we're doing antiderivatives. So we know we want to figure out this exact integral. We have to do an antiderivative to use the fundamental theorem of calculus, part 2. All right, but if we think about doing antiderivatives, we're trying to reverse the derivative process, and going in reverse is a lot harder than going forward. All right, we can take the derivative of pretty much anything using product rules and quotient rules and chain rules, but trying to undo that process is going to be really complicated. All right, so we want to try to avoid having multiplications and fractions and all that stuff in our thing we're trying to take the antiderivative of, because it's going to make our life simple. So when I look at this problem and I see this division bar, I say, oh no, I don't want to have to undo the quotient rule, so that's going to be really complicated. So I instead, when I think about a way I can simplify this fraction and get rid of the fraction before I try to do antiderivatives. And this isn't always possible, but if you can, then it's going to make your life easier. So the first thing I'm going to do is remember that the square root of x is just x to the 1/2. Generally, when you're trying to simplify stuff, it's easier to work with the exponents because you can see how everything works together. And there's this thing that we don't do often, but it is possible, is if we have a minus or a plus sign in the top of a fraction, we can actually split up our fraction into multiple pieces. And we normally do this in the opposite order. Normally we have something that looks like this, and we have a common denominator, so we combine the tops. But now we just did it in the reverse order. Instead of combining the tops, we split up the tops. You can only do this on the top. You can't do it with the bottom. But this tells me that this integral is the same as this first fraction. If I subtract my exponents, I'm going to get x to the 1/2. My second fraction is just 1 over an x, so I just get the negative exponent. All right, so this is the same as my original expression, but I've gotten rid of the division bar. And now it's just powers of x. And I can do the antiderivative of powers of x. I add 1 to the exponent, so 1/2 plus 1 is 3/2. And I divide by the new exponent. The new exponent is 3/2. Dividing by that is going to turn into 2/3. Then I subtract, I add 1 to the exponent. Negative 1/2 plus 1 is 1/2. And I divide by the new exponent, that's 2. And now I want to evaluate that from 1 to 9. So again, I'm going to plug in 9. For x first. I'm going to subtract when I plug in 9. Oops, sorry, not plug in 9, plug in 1, because that's the other bound. All right, 9 to the 3/2 is going to be 27. 9 to the 1/2. The 1/2 is the same as the square root we used at the very beginning. So the square root of 9 is 3. And 1 is nice because it's to any power is just 1. So once you multiply all this out and start combining everything, your final answer you get is 40 over 3. So that's the exact area underneath of this curve with those bounds. Here's one for you to try on your own. 0 to 2 pi of cosine of x. All right, so again, think about your antiderivative, what you're doing, how you're figuring out this exact area, all right, and interpret your answer. And your answer may be surprising. When you take the derivative of, the antiderivative of cosine, you get negative sign. You want to evaluate that from 0 to 2 pi, so I plug in 2 pi into negative sign, and I plug in 0 into negative sign. Both of those give me 0. When I subtract, I get 0. So the area under cosine of x from 0 to 2 pi is 0. And that seems kind of weird. But if I look at the graph of cosine from 0 to 2 pi, it looks something like this. And you can see I get some area above the x-axis and some area below the x-axis. And we know the area below the x-axis is negative. So this negative area down here ends up perfectly canceling out with the areas above, and you just get 0 area. All right, so 0 is actually an answer that makes sense for this problem because the area above the x-axis perfectly cancels out with the area below. All right, so now you know the 2 fundamental theorems of calculus. All right, fundamental theorem normally means it's pretty important. All right, so this is the really big stuff for the second half of the class, all right, is knowing these fundamental theorems. And now that you know those, you can really slay the day.